Good morning, I guess, everyone. So I'm going to talk about the instability of standing wave solutions for the NLS equation star graphs. So it's based on the works with Dmitry Pilnovsky and Troy Goodman, and that was the part of my PhD thesis. So I'll start with the motivation because I think it would be good to start with to explain why the PD on graphs actually have a meaning. So it's started. I think like one of the first mentionings of this PD on graphs been in the Journal of Chemical Physics in 1953 when people started analyzing the free electron models of the naphthalene molecule. And here the idea was that in the naphthalene molecule you have fixed sigma electrons, and then you have these fixed sigma electrons, they make this core, which we call the network. And then there are some free electrons, which are pi electrons, which move along this core. And like here, they move like for example, at this junction point, you have just a continuously go through the point. But at the junction points with free H's, here they have like some complications, I guess, and they try to analyze the behavior of this particle at these points. And later on, this type of models, they appeared in physical experiments when we had some wave propagation in our waveguides, and some multidimensional models. But let's just concentrate a bit on this model from the molecule.
Adilbek.
Yes.
Are the sigma and p electrons, are those the like electron shells, like from chemistry, that I should be thinking of?
Yeah, there is like some like fixed electrons, they just stay, they don't move. But the free electrons, I think it's like from chemistry, I'm not too familiar, but as I understand, it's just there is some type of the interaction between the fixed electrons and the free electrons, and they move somehow, and they found that the electronic motion can be described by the NLS equation in this case.
Do you know if they're the same as the S and P orbitals?
Oh, I don't know. I can tell you.
Okay.
Sorry.
Okay.
Yeah. Yeah. So, and then when we consider the orbitals, the electronic motion, it's just depends on the molecular orbital function of this type. And here you have like this network, and then you just consider the neighborhood of that network, because the free electrons they can't stay on this core. It just moves along that core. But then one can, for the spectral, to analyze the spectral properties or some different properties of the function, they can squeeze the epsilon ball to make the good approximation of this model. And whenever you squeeze it, you just converge epsilon towards 0. And whenever you squeeze it, you end up with a graph of this type with free H's. And here you can just think of each of these psi j to be defined only on the hj. And whenever you squeeze, you also get the connection formula at this point for the functions psi1, phi1, phi2, and phi3. And so here it depends on the connection formula depends on the thickness parameters and the rate of convergence of epsilon. So here are some examples. If you have same thickness parameters with same rate of convergence, you get classical Kirchhoff conditions when you have just the usual continuity condition at the vertex, and you have the flux condition of this type. But if you have a different thickness parameter with same rate, you get this type of conditions, which people call to be a generalized Kirchhoff condition, with some coefficients alpha which appear in front of the functions. One can get more complicated, even like some Robin type boundary conditions at the vertex, if you play with the thickness and rate of convergence like parameters and these values. And there has been like lots of work done in this direction. So so I just pointed out a few of them. It's Kuchman, Zenk, you can see them here, and the recent one by Berkalay, Klatushkin, and Sukhtaev. So this type of models, when we have free edges, it's actually motivates to consider a so-called star graphs. It's a graph which consists of n half-lines connected at a common vertex. And here we've been working with the half-lines only, so it means that here what we have is that each of the branches is a half-line, so has an infinite length. And this is the example with n equal 3, n equal 4 edges. So one can parameterize it, just put 0 here, and this is just R plus each of the branches. The Hilbert space, L2 space, is defined on the graph in the following way. So it's a direct sum of L2 functions on each of the branches. So if you, for example, if you have psi on L2 gamma, then it's just a vector function. Each of the psi j components is defined only on the hj. In this similar way, you can define Sobolev spaces. But moreover, we equip each of these Sobolev spaces by suitable boundary conditions. So for example, for the weaker space, we just get equipped with the continuity, generalized continuity condition of this type. And then for the H2 space, we also add the generalized flux condition, and these two conditions, they give us generalized Kirchhoff boundary conditions. And the good thing about these boundary conditions is that the graph Laplacian, which is defined as the acts on the psi as a second derivative in each of the components, is self-adjoint operator. So the Cauchy problem for the NLS equation of star graph is given in this way. So here you can just consider in general like some 2 pi power, but 2p power. But for now, let's just set p equal to 1. And in this case, the nonlinear term is also defined component-wise. So in some sense, what we have is that here we have like a uncoupled system of equations on each of the branches, but then all these solutions, they are connected using the boundary conditions at the vertex. So it's known that the Cauchy problem here is globally well posed for the initial data being in H1, and the energy and mass are conserved under the NLS flow here. So we're interested in the stationary solutions of this type. So if you just substitute it into the NLS equation, then you end up with the stationary NLS equation for omega and phi omega. One can apply the scaling of this form. Scaling actually makes sense because we have only branches which are R plus, so it doesn't change our length of our branches. But in fact, if you have some bounded, say H, in this case, the scaling also will change the length of the H, right? But we don't care for now because we're only working with the R plus parameterized edges. So, and after the scaling, this phi will solve the stationary equation of this type. And it's known that the stationary equations, they have a Sech solution. And for every n and for every alpha, one can find a particular solution, which is given by the Sech function on each of the h's, and we call it a half soliton state. And if you try to imagine it in the graph, then it would be just basically a star graph with a half soliton on each of the h's. So in many cases, this half soliton state is only stationary state, but one can also introduce some constraint on alphas in order to get a family of other stationary states. So the constraint is given in this way, and it first appeared in the works of Sabirov, Matrasulov in 2010s. They had like several papers that in this subject, and then what's the idea they had is that they partitioned the graph with n edges into k and n minus k edges. So they say that the first k edges are incoming edges and n minus k edges are outgoing edges. And under this constraint with these boundary conditions, they found that if you will move soliton, like if soliton will run along solitons will run along these incoming edges, then they transmit through the vertex completely without any reflections and just keep running along the other n minus k edges. So they did some numerical computations here, and I think they did also like some analytical computations as well. But numerically, it was like no reflection and so on. So based on this constraint, one can find a family of solutions for this stationary equation. And it's also like this, again, Sech functions, but now this is Sech functions which are like translated Sech functions. So it means that you have Sech function, you cut it at some point A, for example, and you either take a left side or right side of the Sech function and put it on the branch. So we call this to be a shifted state. And from this representation, you can see that when A equal to 0, then this is just a half soliton state because it becomes just a H(x) function. So here is the like pictures what we have: 1 equal 3, k equal 1. So whenever A is less than 0, we get picture like this, and A is greater than 0, we get shifted state of this type. And here we can see that because of these alphas parameters at the vertex, like because of this generalized continuity condition, we don't have a continuity. It's just some jumps at the vertices. Okay, so now let's just first talk about the half soliton state, and we'll later analyze the stability of this half soliton state. So just to recap that the half soliton state has this formula, and then for alpha, we just set alpha equal 1 for simplicity, but in general, you can just pick some general alpha. It still will work in this case. And also we consider a graph with n greater than or equal 3 edges. Yeah. So first papers where people started working with the half soliton state, it was in 2012 when Ricardo Adami and his collaborators, they started working with the minimization problem, so energy minimization with the constrained mass. And in this case, they found that the half soliton state is a saddle point of the energy, constrained energy functional. And they did it by just considering two different families. And they found that the half soliton state minimizes the energy within the one family and maximizes within the other family. And because of that, they said that there is a saddle point geometry. It has a saddle point behavior. And but in this case, they didn't relate it with any type of instability. They just, I think, mentioned that there might be some instability in some maybe other work, but it's been more like just. Yeah.
Could you elaborate on this not related to the instability? I mean,
I'll talk. Yeah, sorry.
Wouldn't it imply instability?
Actually, we'll later see. Yeah, it's actually that's what we proved later, that there would be some instability. But I mean, it's not necessarily implying stability because there might be saddle point behavior. But I think there are some cases when you might be
that instability. Oh, I see.
Yeah, of the half soliton.
Okay.
Okay. Yeah. So instability in terms of the orbital instability. So I'll give a definition later. So, and we started now, instead of working with this type of minimization problem, we just decided to work with the action functional, which is given like this lambda psi, which is the energy plus mass. Here usually we have omega parameter, but since omega is equal to 1, we get this thing. The half soliton state is known to be a station as the critical point of this action functional. So if we will expand it later, like with for phi plus complex perturbation, then what we'll have is that we'll get this formula over here. And because of this saddle point behavior and this minimization problem, we would expect that this action functional also has a saddle point behavior. But the interesting thing is that L plus and L minus, we'll later see, they defined in this way, they both are non-negative in the constrained space. So it means that one can intuitively think that if they both are non-negative, then we should probably have that half soliton is actually a minimizer of this action functional. But we will later see that it's not the case because of the higher order kernel of the operator L plus. So yeah, so here the spectral properties of the operator. So we can see that here psi is phi is the H function, so it's exponential decaying function at infinity. It doesn't affect the continuous spectrum, so the continuous spectrum starts from 1 up to infinity. And then L minus is known to be a non-negative operator with the kernel given just by phi, because if you just calculate L minus phi, substitute here, you get the stationary NLS equation again. And phi is completely, it's a positive, right, function. And so L minus has no negative spectrum in this case. L plus is has a unique negative eigenvalue, and the kernel is given by some functions u1 up to un-1. So kernel is n-1 dimensional if you have n edges in the star graph. And for example, there is a particular procedure, you can find it for general n, but for example, n equals 3, you can find that u1 and u2 given in this way. And here I also didn't write it down. Each of these uj is orthogonal to each other, right? So it's the orthogonal family. And for L plus, which is restricted to the constrained space, so if you restrict L plus to the orthogonal complement of the phi, then L plus is non-negative operator. And it's just because if you apply constraint, then your negative eigenvalue, it actually will move, it will increase, but in order to make sure that it just passes through 0, you apply so-called the Vahid-Volkov criterion, which we later, we're not gonna show it here, but it was proven that it all works and it's positive. Negative eigenvalue becomes positive, and you're only left with this kernel and plus extra positive eigenvalues in that case. And so this is our main result on this saddle point geometry for the action functional. So we work only with the real perturbation of phi, and we see that if you just substitute, you don't have L minus function at all here because we don't have complex perturbation in here. And here is our result, which says that if you pick sufficiently small c, then this problem has a unique minimizer. Minimization problem has a unique minimizer u perpendicular, which is unique for every c. And also it's the minimizer h1 norm of this u perpendicular is also sufficiently small. And also we found that it's sign indefinite in C, and because of this thing is a sign indefinite, it means that for different values of C, you might either go below the value of lambda phi or above the value of lambda phi. So in this sense, phi half soliton is a saddle point of this action functional. And here the proof when you just take this function, take the derivative, and then apply the implicit function theorem for that, and you using the implicit function theorem, you find that for every c there exists a unique minimizer. So in some sense, this u perpendicular is a function of c, and you can show that this expression, this estimate holds for the u perpendicular. So, and then later, in the case of unique minimizer, when you like take this u perpendicular, it minimizes it, you can find that this difference actually can be written as cubic term plus terms of the order 4, and the cubic term was found to be given explicitly by this formula. In order to show that this cubic term never like vanishes, we just compute just one of these terms, namely the term is when you have cj's cube, and then you find that for j greater than or equal to, this inner product never vanishes, and so it means that you always have this cj cube terms in this expansion and this expression. And so because of these cubic terms, you can find that m0 is sign indefinite, and since it's the leading term in this expansion, then MC is also sign indefinite. So that's kind of gives you saddle point behavior. And here is the example for n equal 3 case. You can just find m0c to be equal to this, so this p equal 1 to be equal to this function. So now, because of this saddle point behavior in the action functional, we expect to have some instability, some orbital instability as well. And its orbital instability is given just, yeah, so this is the definition of orbital instability. So basically the idea is that whenever you start in the some small neighborhood of the half soliton, if your global solution always remains in this orbit of the half soliton, in the small neighborhood of the orbit of the half soliton, then you say that your stationary solution is orbitally stable, so it never leaves the orbit of the half soliton. Otherwise, if you go beyond the orbit, you just say that it's orbitally unstable. So, and that's our main result on the instability of half solitons. We just show that the half soliton is orbital unstable. So it means that there is this time t0, there is some initial data v such that the v is sufficiently small, but it always goes at some time t0. It always goes beyond the epsilon neighborhood of the orbit of the half soliton. And then the proof is actually will consist of the several steps. So we'll use the energy method just to show that all our most of the terms in our evolution system would be very small, and then we'll reduce it to the final dimensional system. We will show the connection between the original system and that final dimensional system. So let's just start with first expansion. So here we just show that whenever your solution is in the around the orbit of the half soliton, then you can always expand it in this way using the modulation parameters here under these orthogonality conditions. Then you can substitute this expansion into the NLS equation, and you will get the time evolution system for the perturbation terms here. And next step would be like we will show that this term, so theta dot minus omega and omega dot, they are small. So we just apply the orthogonality conditions, this and that, to this equation, just taking the derivatives with respect to time here and there. We will end up with the following system. And here we see that assuming that omega u and w are sufficiently small, then this thing here would be of order 2. This and these terms, the diagonal terms would be small here. And here, these things would be some number, right? Because the inner product of derivative of the half soliton with respect to omega and half soliton is actually some constant number. It's not constantly changed with time, but it's of order 1, right? And so this matrix is invertible, so you just apply the inverse to these terms, and you'll end up with these estimates over here. And now next, since we said that in the expansion, we won't always set omega to be equal to 1. We'll just start with omega equal to 1, and as time goes, omega just will go, and then we'll just move around 0.1 mostly, as we'll later see. We just say that L plus here would also depend on omega, and I'll just show it over here. So here L plus is the value, this is the value of L plus for the omega equal 1, but when you have general omega, then omega will appear here instead of 1, and here you'll have phi omega. So that's the changes which you will have for the L plus there, and for the L minus. And we say that since we know that the kernel of the L plus is n minus 1 dimensional, we just call the orthogonal basis of this kernel to be uj omega. And then we also introduce wj omega, which solves this equation. And this equation can be solved because u omega is orthogonal to the kernel of the operator L minus, right? So you can solve them. Next, we decompose our u in this way and our w perturbation term in this way. So here you have the orthogonality conditions for u perpendicular and w perpendicular of this form. And next, we will try to show that these perpendicular terms, u perpendicular, w perpendicular, they always remain small. And in order to do that, we apply the energy method. So we first consider the action functional, and we just take the action functional with respect to w. So that's what we have with respect to omega. Sorry, that's what we have. So omega changes. We yeah, so we have this thing, and then if you expand, then you will have that the action functional can be expanded in this way, with the omega dependent on omega 1 squared plus cubic term, and L plus u quadratic forms for the L plus and L minus plus some high order terms. So later we substitute the decomposition of u and w, which we obtained previously, in terms of uj w omega, wj omega. we substitute it here, and we end up with the decomposition of this type. And here, the good thing with this is that L plus omega and L minus omega, they are coercive for the U perpendicular and W perpendicular in this case, because they are orthogonal to the kernel of the L plus, for example, and so it actually moves the minimum value of this quadratic form to be like bounded by a positive constant times h1 norm of these terms. And so it means that this value, this action functional, is bounded from below by the constant multiple of omega minus 1 squared plus constant multiple of this h1 norm squared plus some extra terms over here. And so in order to get that this omega minus 1 and these terms are very small, it would be nice to get a bound from the upper bound for the action functional. That's what we get using the conservation of mass and energy. So we just rewrite the action functional in this way. So because energy and mass at any time t is the same as energy and mass of the initial data. So we use that. And here we use that, we just say that assuming that our initial data is located in the delta neighborhood of the half soliton, we have this estimate, and because of that estimate, we can compute that delta 0, which is a constant of motion here, plus this term is less than some constant multiple of delta squared. And then we combine this formula with the coercivity result which we obtained here, and then for the omega minus 1 squared. And what we have that omega minus 1 plus the h1 norm of these things would be less than delta. So it was delta squared, but here we had omega minus 1 squared, so I just removed all these squared values. So delta, and here you have b, and here you have c cube. It was m0c, it was this previous sign indefinite function, so which is c cube. So we just get that omega minus 1 plus this h1 norm is less than a constant multiple of delta plus c cube over 2, so it's just c and the 3 over 2 plus beta plus b. Next, so we obtained that this term is very small, and we know that these terms are small. And so what we do next is we just substitute the decomposition of u and w into the this time evolution system. And then what we have is that we get the time evolution of the system, like this time evolution for the Cj, Bj terms, and also for U perpendicular, W perpendicular terms. Then we apply our orthogonality conditions that U perpendicular is inner product of U perpendicular with each of the Uj's is equal to 0. And same for the W perpendicular. We end up with the following system for the following system. We have this thing, and here we do a truncation. Like first, it's a kind of formal truncation, but we'll see later that actually it will make sense. So the idea is that here this is of the second order term. So each of these is at least one first order term. So it means this entire thing is the cubic of the cubic order. This is of the cubic order, and this is of the second order. But so what we did is just for the truncation purpose, we just forget about this thing, and we will take this as the first equation, that this bracket is equal to 0. And then for the second system, what we do is we also apply truncation, but here this is cubic term, this is again cubic term, but for the RW, it's a quadratic term plus other cubic terms, so we just take the leading order of this inner product. And we end up with, also we just say that omega is equal to 1, so since we know that omega minus 1 is also small, we just truncate with omega equal 1, so we just take that as part of expansion. And so we have this Hamiltonian system, and for this Hamiltonian system, what we have is that the Hamiltonian is given in this way with m0, which was previously given to be signed indefinite function. But here we can explicitly calculate that each of these, for each j, this inner product is positive. So it means we will have some positive beta j squared, sum of this beta j squared, plus some sign indefinite cubic function. And one can show that there exists some zero equilibrium, there is some unstable direction from the zero, from the neighborhood of the 0 point. And one can also show that whenever you will try to, we'll try to start in the neighborhood of 0, then eventually in the time of order epsilon minus 1 over 2, you will go beyond the orbit of the epsilon neighborhood of 0, right? So it means that it's some type of the very slow instability in this case. So this is a result for the truncated system. But now we will show that whenever you consider now the full system for the C and B, then these solutions CB of the original system, they remain very close to the solutions gamma and beta of the truncated system. And for that purpose, we just consider the like a not a square but rectangle for CT and BT. So we just show that in this, if you are inside of this rectangle, picking our initial data to be delta, such that delta is equal to epsilon 3 over 2, we can get that the terms omega minus 1 and u perpendicular, w perpendicular, they remain very small in this case. And so using that result and the Gronov inequality for the norms of the CT minus gamma t and BT minus beta t, one can get that these solutions, they are very close. So it means that the norm of CT minus gamma t, for example, is less than the constant times epsilon 3 over 2. And because of that, whenever you, for example, if you take epsilon over 2 level, then whenever gamma t leaves this epsilon over 2 level, C of t also leaves this epsilon over 2 level because of very close, because they're located very close to each other. And so it means that whenever you leave the epsilon neighborhood, whenever the truncated system leaves the epsilon neighborhood, the original system also leaves the epsilon neighborhood. And that gives the nonlinear instability of the half-Solton states. And also we see that it's very slowly growing perturbations, and it happens within the time of order epsilon minus 1 over 2 in this case. Okay, so that's actually concludes here. I conclude with the nonlinear instability result for the half-soliton. And now another part which I want to talk about is that this nonlinear instability of half-soliton is actually also implies the instability of the other shifted states of the particular form. And so I'll just talk about it here. So for now, let's just assume that k is equal to 1, and the constraint is equal to this. Constraint is given in this form. And so it means that if we will now reparameterize our incoming h associated with the first h to be not 0 plus infinity, but to be minus infinity 0, then the entire equation might be nicely given, stationary state might be nicely given in this following form, because previously you had x minus a, but after reparameterization it would be x plus a over here. And so this is just to remind you what we have. So here k equal 1, and so for a less than 0 we get this thing, but for a greater than 0 you get this thing. Okay, and now the L plus and L minus operators, which we've been working previously for with the half-Solton, in the half-Solton case, they now depend on the A, and the dependence on A is actually incorporated over here, since our function, our shifted state f depends on A. But anyway, since it's a CH function, it's also growth. Again, it's just decays exponentially at infinity. The continuous spectrum remains the same. L minus has the same properties. It's non-negative with the kernel given by the shifted state. And here there are two cases. First is a less than 0, another is a greater than 0, but we're interested in the case a greater than 0. So it's this case, I'm sorry, it's this case when you have just one bump and all the other things are without bumps on the other branches. Oh, I missed this. Yeah, okay, I'll talk about this. And in this case, A is, for the A greater than 0, we have one negative eigenvalue of the operator L plus. And we found that in this case, when A is greater than 0, we have one negative eigenvalue. Then the shifted state is spectrally stable. So I won't talk about spectral stability now. It's just the result, and it's just distinguish between this case and the other cases, because all the other cases are spectrally unstable. But here it's a spectral stable, and it's interesting to work with that, because later we'll see that even though it's spectrally stable, it's nonlinearly orbitally unstable. And so if we'll keep working with the spectrum of L plus, we can find the interesting behavior of the spectrum depending on alpha, or depending on A, translational parameter. So the continuous spectrum, as we said, starts from 1 up to infinity. We have only simple 0 eigenvalue in this case, and we have simple negative eigenvalue, which is actually -3, can be found explicitly. And there is also eigenvalue lambda 1, which depends on A in the following way. So we can see that when A is equal to 0, we are at the half-Solton state, and this eigenvalue has multiplicity n-2. Then at half-Solton states you have n-2 plus 1. So you got n-1 dimensional kernel. But if you are not in the half-Solton state, then you have a simple 0 eigenvalue. And then if A is less than 0, you get a highly dimensional negative spectrum here. But if A is greater than 0, you have only one negative eigenvalue here, and all the other eigenvalues are positive. So, and here, yes, I missed this slide, I'm sorry. So the idea is that what happens, why do we get this nonlinear instability in terms of the orbital instability, is because of the momentum functional is not preserved under the time flow, because usually in many systems, like for example for the NLS on the real line, you have that the energy norm and energy mass and momentum, they're all conserved. But in this case, because of the graph structure, it's not translationally invariant, like not always translationally invariant. For example, shifted state is translationally invariant, but in general, if you have some other type of function, because of this type of continuity conditions, whenever you move your solution, it might break this equality at the vertex. And so it means that kind of translation breaks the solution, and so the solution, the function won't be in the H2 gamma space in this case. And so we can find explicitly that if you take the derivative of the momentum functional with respect to time, then it's a monotonically increasing function. And here is the result that will later show that this monotonically increasing behavior of the momentum functional is related to the behavior of the translational parameter A, and it's given by this theorem. So we just say that if you start with some A0 greater than 0, then whenever you start in the delta neighborhood of the orbit of this shifted state, localized at A0, as time goes, your AT, like your translational parameter, it moves towards some nu. You can just take nu to be very close to 0. And then in time, what we get is that whenever you move towards the vertex, towards the nu, you still remain inside of the epsilon neighborhood of the orbit of this shifted state localized at AT. So I think it's a bit complicated. Maybe I said it very in a complicated way, but it's better to see it on the picture. So here is the example with n equal 4, k equal 1. And so the idea is that if you are localized, if your Solton is localized at point A0 over here, then as time goes, you just keep moving towards the half soliton, and whenever you keep moving towards the half soliton, like you will get that this part of CH will appear, and eventually you will end up with a function which is very close to the half soliton state, right? Okay, and then and here is the proof of this fact. So since you have the translational parameter, you add one more modulational parameter AT over here. Using this, so you get more, like, use more orthogonality conditions for that purpose. But the idea is that you substitute this psi into the NLS equation. Again, you get the equations for this matrix type equations for this term, and that term, and you can extract that A dot, the equation for the rate of change of the parameter A, and it's given in this way. And here, another thing to notice is that when you expand the momentum function, it's given in this way. So it means that the leading terms here, they are just have the opposite sign, but they're the same. And so you just combine these two formulas, and you get this type of connection between the monotonicity of A and the momentum functional. And so since we said that momentum functional is always increasing function, we can say that if momentum functional at the initial time 0 is positive and it's increasing, then this derivative of A becomes, like, always remains negative, and so A will decrease, and so it will, like our soliton will move towards the vertex in this case. And that's what we have. That's what I said. The initial datum, you can pick it in such a way that your momentum functional is positive in this case. And since momentum functional is non-negative, non-decreasing function, you'll have that momentum of the psi always will remain greater than or equal to the momentum of the initial data. And because of that, and the previous connection between the derivative of A and the momentum functional, you will see that you can adjust these epsilon and delta parameters in such a way that the rate of change of A would be always bounded away from 0. And so it means that you will just move towards, A will move towards 0 without, and the rate of change won't decay, right? It's just will keep moving, and eventually will reach the value nu, which has been, like, for example, around 0 in this case. And here again, some numerical simulations, what we had, which we had. So you start over here. So the idea is that you are localized on the H1. Oops, you're localized at the H1. At the point minus 0.55, so it's over here somewhere. And as time goes, you see that you just perturb it, and then you see that the localization, like the soliton, actually starts moving towards the vertex, and it starts appearing on the H2 and H3. And after, like, some long time, just after 40 seconds in this case, what we'll have is that it crosses the vertex over here. And then it means that in this time it's in the neighborhood of the half soliton, and once it crosses the vertex, it eventually just runs along the H2, and it just goes away, and that leads to the type of the instability in this case. So yeah, thank you very much. So that's the end.